Marta and also for inviting me to give this lecture. The title of my lecture is Multi-Messenger Astrophysics, which I would say that a few years ago, from a theoretical point of view, was considered quite a broad subject. And since some years, it became a reality. Of course, I will present, a part of the story, also given the fact that we don't have so much time. But so let's go to the, let's say, very brief introduction. Okay. So if we want to define multi-messenger astrophysics, we can imagine this as a kind of a triangle whose vertex are occupied by fundamental messengers. So as you all know, we can think about a messenger, which you are almost very familiar with, which is the electromagnetic one. And on the other side, we can have the gravitational messenger. Here you see, for instance, the two cases. This is the afterglow of the binary neutron star event 1708-17, and this is its electromagnetic signal. On the other side, you see the other type of messenger, which so far has been connected, which is that of neutrinos. In this case, these are the traces in the ice cube detector of the high energy neutrino detected on September 2017. And this is the sky map of the high energy source, a blazar that was associated with this event. Of course, I think the holy grail of this study is that of connecting these three vertices, establishing, of course, connections which at the moment are envisaged, but not yet a reality. So just to give a brief summary, on the one side, so on the side of connecting gravitational waves and electromagnetic signal, I think the lesson we should refer to is that of the first gravitational wave from a binary neutron star merger that was followed 1 seconds after by a short gamma ray burst. There was the detection of a fast optical near-infrared transient, which is the kilonova, and a long-lasting, detected past 1 year, also very recently, that is the non-thermal emission associated with the outflow, the relativistic outflow. The lessons, the physical implications of this discovery are really wide. So we can learn about the physical properties of the neutron stars. We can at least make a sign, put a signpost on the fact that, as we expected, the short gamma ray burst can be produced by binary neutron star mergers, that these sources, binary neutron star mergers, are indeed contributors of abundances of high elements, and that a fundamental part of this game is played by the possibility of producing a relativistic jet. For what concerns the other side of the triangle, we know that you know that in September 2017 there was this discovery of a very high energy neutrino, and this is not the only one, but this is the first one with an associated electromagnetic counterpart, which is this blazar, so an AGN with its jet nearly aligned with the line of sight. And by archival study, it was also suggested that from the direction of this blazar, there could be an excess, let's say somehow correlated with flaring activity, highest, let's say, electromagnetic emission phases of this event. The implications are also in this case extremely wide, because studying neutrinos and their possible origin is, of course, a way of accessing the physics of cosmic accelerators. of places and where the highest energy particles are accelerated, and so the link between neutrinos and cosmic rays can be established. Now, let's say that if we want to fill the triangle with the putative sources which are responsible for these signals and their interconnection, of course, we have to think about the fact that there are some requirements. We should deal with sources in which there is the possibility of accelerating particles at really extreme energies, in which, in a way, there is a lot of amount of power channeled possibly into some kind of collimated outflow. And there is a lot of energy in terms of emitted photons. So there are different sources, some of which have already been spotted, that goes from massive black holes, very massive black holes at the center of galaxies, to stellar mass black holes, either in isolated or as the product of the merger of compact objects. As I said at the beginning, probably the holy grail here is to find a combined multi-messenger 3, which is the title of this slide, which is combining the 3 messengers into a single shot, which would be obviously a fantastic discovery, and probably something that will happen, we all hope, soon. So this is to introduce, let's say, the subject. And now I'd like to tell you the plan of these 2 lectures. So I thought about dividing the lectures into 2 parts. Today, I will mainly give an overview of gamma ray bursts. The reason being the fact that, as you probably are all interested in gravitational wave sources and their electromagnetic counterparts, this is a gamma ray burst. The source that produced at least 2 of the electromagnetic emissions that were identified in the only but first BNS, which is the prompt gamma ray and the afterglow. Tomorrow, instead, I will devote the lecture to a more detailed discussion of indeed the 1708-17 electromagnetic emission, both the prompt and the afterglow, and the kilonova. The approach I thought could be, I hope is suitable for this school, is that of having a simplified observational picture, which of course is only a partial view of all the let's say, properties of these sources, but is, I hope, enough in order to build together a simplified physical model. I organized the lectures with this scheme, so you have always the title, and at the bottom, a kind of a take-home message, which summarizes the main concept of the slide. And I'd like to apologize, first of all, before starting, for the fact that in both fields, especially, you probably noticed that since 2017, there was a flourishing of an incredible amount of papers devoted to this source. And of course, it's impossible to cover them all. It's a personal selection, and I apologize for any missing reference, which of course is fundamental, but there's no space. I tried to make a short list, which of course remains to you with the lectures, of these 5 references, which are, in my opinion, very nice reviews on the different topics that I will try to touch during these 2 lectures. So for any, let's say, further information you may need, you can go to these reviews, where you can find, as any review, probably starting information and a lot of references to go deeper into the subject. Okay, so as I said, the first lecture is devoted to gamma ray burst. I will give a presentation which is valid for both long and short gamma ray bursts. Of course, for the present gravitational wave counterparts, we are mostly interested in short GRBs, but despite the differences in their observational properties, there are many similarities, and This is, let's say, let us build up a model which at first approximation is valid for both classes. The reason also is related to the fact that given the larger luminosity, we have much more information also from a statistical point of view for the class of long GRBs. And so it's a kind of an extrapolation to the class of short ones. Okay, the first, I will start from very basic definition, but here the nomenclature is important. When we talk about gamma ray bursts, you probably all know that we typically use these two terms, prompt and afterglow, which characterize and describe two different and separated in time emission phases. The prompt emission of a gamma ray burst is the emission that is characterized by the emission of high energy photons. And this is, let's say, what made gamma ray bursts be discovered and what made them be serendipitously discovered starting in the 70s. We know since the end of the 90s that this emission is accompanied and followed by long-lasting emission that pops up at different frequencies spanning all the electromagnetic spectrum from the X-rays down to the radio band, which is called the afterglow. So the bottom line is that GRBs, as you know, are multi-wavelength emitters. They are transients, and let's say, being transient is different if you consider the prompt and the afterglow phase, because of course, these are characterized by different time scales. A possible, let's say, summary of the gamma ray burst history in a single slide is represented through these steps. So let's say we know these sources since 50 years, but the understanding of their physics was somehow built up through the years, thanks to what I think are the milestones. So since their discovery in 73, we go to 1992, when one of the main results of the Compton Gamma Ray Observatory was that of showing that these sources are isotropically distributed in the sky, thus suggesting that they could have a cosmological origin. The confirm of these came in 1997 with the discovery of the first afterglows, which allowed to pinpoint the location of the source, take a redshift from ground, and demonstrate indeed that these are at cosmological distances. In 1998, soon after, there was the first detection of, let's say, somehow particular supernova-like event associated with the first gamma ray burst, and then others came. And this was a demonstration that long gamma ray bursts are somehow associated with the hypernovae event. We then go to 2005, when the Swift satellite started to unveil what happens at the very beginning of the gamma ray burst, let's say in the transition phase between the prompt and the afterglow, highlighting several different properties. And of course, due to its agility, let's say, it was able to collect a lot of redshifts and therefore allow, let's say, cosmological population studies. In 2008, the Fermi satellite started to explore much better than what was done with the Egret on board the Compton Gamma Ray Observatory, the very high energy of these sources, meaning photons with energy in the GeV band, which is important for different reasons, especially for the understanding of the physics of the acceleration of particles, which then emit photons through synchrotron at such high energy, synchrotron and inverse Compton. As you know, in 2017, we had the first evidence of the fact that short GRBs can be somehow produced by the merger of compact objects, in this case, two neutron stars. So we had the first evidence of the progenitors, also the long-awaited evidence. Even recently, starting in 2019, the MAGIC telescope on ground was able to finally discover the very high energy emission at TeV energies of GRBs, which shows the presence of the second hump, which much like other, let's say, powerful sources like Blazer, is interpreted as the inverse Compton component of the synchrotron emission. This is just a very brief description, but let's say the bottom line here is, I think, the fact that if you look to the time scale and to the fundamental observation, you understand that most of the fundamental advancements were signed by new technologies, new satellites, or opening of new windows by ground or space-based facilities. Okay, so let's start smoothly with a bit of a more detailed description of the prompt emission of a GRB. Here I show you one example in order to let you see within this light curve of the prompt emission counts as a function of time, the fact that different time scales coexist. You have, you can recognize immediately the total duration of the event, which is about 60 seconds. You can see that there are different pulses which are separated by quiescent phases. And you probably can see that there is also a very short variability of the emission, which is characterized by these short spikes, which can be, in general, with the duration of a few milliseconds, few tenths of milliseconds. If we take the first time scale, so the total duration, you know that gamma ray bursts can be divided into short and long. This is the distribution of the total duration, let's say a proxy of the total duration of GRBs, which has this bimodal distribution with an observer frame separation of about 2 seconds into two classes, short and long. The ratio between the number is about 1:3 or 1:4, depending on the instrument. So shorts are typically identified as GRBs with a duration lower than 2 seconds and long ones larger, with an average value which is 0.5 and 20 seconds respectively. Already in the 90s, when people started to study these sources, tried to, for instance, build up a plot like this, which is a bidimensional representation showing the correlation between the spectral property here in the y-axis, which is an hardness ratio, basically the fraction of number counts in two separated energy ranges as a function of time. And as you see, the class of short GRBs and long GRBs, so green and blue, have slightly different hardness. Apparently, there seems to be a kind of a paradigm with short GRBs being harder than long ones. And this was one of the first hints of the fact that these sources could have a different origin. To go into a bit more details, you can look to this graph, which shows the variability time scale measured in some way. There are different ways as a function of the duration. Here you see in blue some short GRBs and in red some long GRBs. You see that, of course, the variability is much smaller than the duration represented by the equality line. In general, you have a variability time scale of the order of a few tenths of millisecond for short and 100 of millisecond for long gamma ray bursts on average. What is important here is that if you think about the variability time scale in terms of causality argument, you immediately understand that the region which is responsible for the production of photons should be a very compact one with the dimension, linear scales of the order of 10 to the 7, 10 to the 8 centimeter approximately, okay? This is an important point because it's the first hint of the fact that the sources responsible for this emission should be quite compact. Okay, I think this is enough for the moment for what concerns the prompt emission properties. The other ingredient in order to understand these sources is to see how the energy is distributed, how the emission, so the flux, is distributed over the energy. So to see a spectrum or a spectral energy distribution. This is shown in this plot here. So to confuse you, now I hope to be clear enough. Here you see the first plot here is a photon spectrum representing the flux of photons per unit area, unit time, and unit energy as a function of the energy. As you can see, the spectrum is extends over 4 orders of magnitude, and it is non-thermal. What does it mean? It means that its curvature is much broader than a typical blackbody-like shape. The spectrum is featureless, as you can see, and it is typically described by 2 power laws, which describe the low energy part of the spectrum and the high energy part of the spectrum, and the connection between these two is smooth rather than sharp. If you multiply the flux or photon spectrum by the square of the frequency, you get the so-called nu-f-nu spectrum, or SED representation of the spectrum, which is a very useful way to describe these sources. Of course, depending on the slopes at low and high energy, but for typical values, what ends up to be is that the nu-f-nu spectrum is rising at low energies, because typically the low energy spectrum is has a photon index which is larger than -2, and whereas on the high energy part, the photon index is smaller than -2, and for this, by multiplying by E squared, you end up with this, let's say, peaked shape. What is important here is that this representation identifies indeed a peak, which is one of the fundamental prompt emission parameters we typically deal with. In this case, but in general, this is true for a larger fraction of GRBs, this peak energy is at around 1 MeV. This is important because this energy represents the typical energy of the photons emitted by the source. And so if we want to understand what is the emission process, we have to deal with this numerical value. Now, don't have time to show you let's say the results, but if you trust me, we can make an initial comparison also in terms of spectral shape between long and short GRBs, which is schematically represented here in this plot. In general, they have a similar peak value in the nu-f-nu representation, provided that you correct for the different redshift, okay? But the main difference instead is in the low energy part of the spectrum, which for short GRBs is typically harder than long ones, which are softer, okay? And this is say an observational signature which is still not fully understood. And in the recent, I would say in the recent years, became, in my opinion, at least for me, an interesting subject of research. Now, I think that with these ingredients, at least the short time scale variability and the shape of the spectrum, we can first, we can try to enter a bit more into the, let's say, physical ingredients we need in order to understand these sources. And one of the first one we have to deal is the fact that GRBs are relativistic sources. What does it mean? It means that, as we know today, these sources are able to produce a relativistic outflow within which photons are produced. And being produced within a relativistic outflow, of course, everything we see is subject to relativistic transformations. Why do we know that? I think that the easiest way to understand this from a theoretical point of view is to rely on the so-called compactness argument. So here you see, again, the spectrum I was showing before, and you might imagine that for the moment, these sources are isotropic. So you have the central engine, and you have a shell of material, which is spherical, which is producing the photons you see. Now, if you see these photons, you should be sure that and you are sure then that the source is optically thin to is transparent. And as we deal with high energy photons, because the energies here, as you can see, are MEV energies, the main source of opacity you have to check is not affecting the emission of the source, is the gamma-gamma opacity. So the gamma-gamma annihilation producing pairs. In a very simple way of dealing the problem, which is not, of course, the, let's say, formally most correct one, but as at an order of magnitude is sufficient, you can think that the optical depth is the product of the cross-section, approximately the Thomson one, times the density of photons. Of course, the larger is the density, the larger number of photons are packed in a small volume. You can imagine the larger is the probability for them to annihilate, and therefore the larger is the opacity of the source, times the size of this shell in this very schematic way. You can plug in the number of photons by simply dividing the energy that you see in the prompt phase divided by the volume and by the characteristic energy for photon-photon annihilation. This is, as you know, related to the fact that each high energy photon can annihilate with a low energy photon, which it has an energy so that the product of the two energy is larger than the electron energy squared. And in order to, let's say, have something related to the observable, we can substitute the radius here with the variability time scale. So if you plug in the typical values, and by the way, now and in the following of the lectures, I'm using this notation, meaning that in doing this numerical calculation, I used an energy of 10 to the 52 ergs and a variability time scale of 10 to the -2 seconds in this specific example. You can see that the gamma-gamma opacity is 3×10 to the 16. This is extreme, and this is a paradox. This is, in fact, was called the compactness argument or paradox, because if these numbers are correct, we should not see any high energy photon with the energy epsilon2 should not escape the source. So instead of seeing this very smooth spectrum with this high energy tail, we should see a spectrum which is cut more or less at an energy modulus, of course, the redshift and at the electron energy, characteristic energy, rest mass energy. So this is a paradox. How to solve that? Of course, invoking relativistic expansion, because if this source is, if the shell, instead of being static, is expanding relativistically with a Bike-Lorentz factor, which is gamma, you have to introduce the relativistic correction to this argument. The first one is affecting the energy threshold for photon-photon interaction, and in the form that, of course, if photons with energy epsilon1 and epsilon2 annihilate in the co-moving frame, the observer does see the photons with, let's say, an enhanced energy, which is a blue shifted energy, each one by factor gamma. So the photon-photon threshold, therefore, transforms in a threshold which is shifted by a factor gamma square. And this first effect, of course, makes, let's say, the number of photons that can produce pairs lower, because you are shifting, let's say, the target photon energy on the part of the spectrum which is, let's say, which is characterized by a lower number of photons. The second correction is instead in the variability argument, which should be computed taking into account the Doppler factor, and you have another gamma square factor here. By using this transformation and let's say representing the high energy part of the spectrum, which is the one affected by this gamma-gamma interaction, by epsilon, the energy to the power beta, you end up with this relation between the opacity in the relativistic case and the opacity in the non-relativistic case, the one that we computed before, which is this one. And you see that there is a relation times a factor, which is gamma to the power 2 beta minus 2. For a beta, which is typically around 2, you have a power gamma to the minus 6 here, which reduces substantially the opacity. Now, what we have is that for the gamma factor of about 100, you are able to make the opacity, let's say, comparable with 1. So this means that in order to justify the fact that we see very high energy photons, and so in order to have the gamma-gamma opacity equal 1, you can just assume a gamma factor which is larger than about 200. This was the argument, a theoretical one, that was first in favor of the relativistic motion. But if you are not convinced, you can ask for observational evidences. Okay, and this comes all. Yes.
Can we just stop just for a second? I want to check whether you're using your pointer, because it seems it does not appear on the slide anymore. I don't think it's a yes. So that's okay.
Now,
yes. So now we see it. We did not see earlier, but I don't think it was a problem because your slide is, you know, fairly linear, and I think it was okay to follow what you said. But you should know that now we see your pointer, and I think this may help.
Okay.
Can I take just this occasion to perhaps ask the whether there are any question? We did not have questions so far. Would you be okay to have a first quick round of questions?
Yes. Whenever, sorry, I forgot to say, whenever you want to interrupt me and ask, whenever I'm not clear, please interrupt me, and I try to repeat or make it clear if I'm able. So yes, interrupt me whenever you want.
Right. So I'd like to ask the attendants here whether there are any questions for Giancarlo so far for the first half hour. It seems it's all clear so far. So just wait for.
Can I ask a question, Giancarlo?
Ciao, Raffaele. Yes.
Oh, ciao. You talked about the prompt timescales in the beginning of your introduction, and I was wondering if there had been any Fourier transform studies of prompt emission to study the different timescales, you know, on a analytical range rather than just at given timescales.
Yes. To my knowledge, these studies were done mainly in the past because you need high time resolution. And there were studies that by constructing the power density spectrum highlighted the fact that you have a typical slope for stochastic processes within that during the prompt. I'm not aware of recent works but probably I missed it, with Fermi. So what I'm saying dates back to works with Bazzi, and from a more, if you want, detailed point of view, I haven't seen any so far. I'm not aware, at least, of any study which tried to study the possible, let's say, Fourier transform on different energy ranges, because there seems to be a strong dependence on the time scale. I made it very simple on the energy range. For instance, the fact that at higher energies, there seems to be a shorter duration of the pulses whenever they can be studied individually with respect to the low frequencies. Mm-hmm. High frequency and low frequency, I mean, very, let's say, MEVA range with respect to X-rays, so a few kV.
Okay, thank you so much.
Thank you. Ilsan, do you want to speak up?
Yeah, just quick question. You showed that the prompt emission at the observation, but I was wondering whether the instrumental time resolution is sufficient enough to capture the the variability fully, or is it, do we need more, finer time resolution, or are we already good enough?
Well, of course, one would like to have the highest resolution possible. The limiting is that time of the instrument, which for instruments like scintillators-based instruments like the one on the Fermi satellite, the GBM, or like BATSE, can be as small as a few microseconds. The problem, as far as I am aware of, is the fact that even though you have a very short timescale, a very short, let's say, measuring timescale possibility, you, however, need a lot of counts on that timescale in order to have enough statistic for whatever you want to do, like, for instance, building a PDS. So you are, in a way, obliged to combine timescales, so you cannot work at the highest temporal resolution because you are limited by the statistics. To my knowledge, in the future, probably there won't be a substantial advancement in these, so we will be dealing, except maybe with the microsatellites like those that are thought for studying, using, for instance, also gamma ray burst for fundamental physics studies, but this is another story, like Hermes, but maybe it's becoming too long. But I hope I just give you a satisfactory answer for this.
Yes, thank you very much.
I don't see other question in the chat, so I believe we can resume the lecture now.
Okay. Okay, so the proof that GRBs are relativistic are coming, direct proof or indirect, are coming from the radio band. First one was an indirect one, was the scintillation evidence, which is represented here. So the fact that the radio light curve was highly variable up to about 20-25 days, and then it became quiet, was interpreted as due to the fact that the source size before 20 days was smaller than the scintillators projected size, which are interstellar clouds along the line of sight. When the source has become larger than that size, than the projected size of these clouds, gas clouds, of course, the scintillation is suppressed. In this interpretation, it is possible then to derive the speed at which the source expanded. More direct evidences instead were obtained by measuring directly the angular size of the source as a function of time. For instance, in this burst here, that up to nearly 10,000 days is 1,000 days, it was possible to see a considerable expansion in the size, sorry, growth in the size of the source. Or, let's say, the fantastic evidence of proper motion of 1708-17. There is a big difference in these probes. These are direct, this is an indirect probe, but they work, of course, due to the limitation of the instruments and the, let's say, flux level density of the sources. These kind of studies are possible for very local events because they should be, let's say, they should be resolvable in a way for measuring the angular size, or the astrometric position should be precise enough to measure proper motion. Whereas for radio scintillation, we can work even with more distant sources at the expense of the fact that the interpretation of radio scintillation is not totally unique. I mean, it's a bit more complicated because you can have different ways, different physical processes that contribute to the variability at the early stages. The second ingredient that we have for, that we need for GLBs is the energetic. Now, in this plot here, you see the isotropic energy. So assuming that these sources emit in all directions equally as a function of redshift, sorry for the different colors, but you can recognize long GLBs are red and blue, and a few short GLBs which are green here. This just to show you that, of course, these sources are extremely powerful, ranging from a few 10 to the 49 to 10 to the 54 ergs emitted during a time scale, which is that of the total duration of the prompt emission, which is a quite large amount of energy in terms of equivalent masses. As far as their distance is concerned, here you see a plot comparing the redshift distribution of short and long GRBs, which is quite different. Long GRBs have an observed redshift distribution, which is not the intrinsic one probably, because it's of course affected by selection effects, peaking about 2, whereas short GRBs are peaking in redshift below 1. And now we know that very likely this difference is intimately related to the different progenitors, as long GRBs being produced by massive stars, they trace more directly, let's say, the cosmic star formation rate due to the small delay between the formation of the progenitor and its core collapse, whereas short GRBs have a considerable delay between the formation of the binary object and its merger, which can be of several mega years up to a few giga years. Still related to the prompt emission, we have important informations when we try to correlate the peak of the spectrum, so the peak of the SED, which tells you where most of the energy is located in terms of photons, and the total energy of the prompt emission. Here you see two correlations which are very much used in the field of GRBs, which relate the peak energy in the rest frame of the prompt emission with the isotropic energy. And the gray points are long GRBs and the open squares short GRBs. The slope is more or less a peak energy proportional to the square root of the isotropic energy. Here you see the same peak energy now correlated with the isotropic luminosity. There is a slightly difference in the position, relative position of long and short GRBs. Starting from this plot here, you see that more or less long and short GRBs follow a similar relation. They also occupy the similar position in the plane, whereas in the peak energy versus isotropic energy plane, short GRB seems to be displaced, even though apparently they follow a similar correlation. These two bursts here are probably accounted for being, let's say, transitional objects which are in between short and long GRBs. Because as you saw, it's hard to separate the two populations being overlapped in their duration distribution, of course. Last point to say here is that the bottom line is that these two correlations are basically saying that the harder is the spectrum, the peak of the spectrum, and the more energetic or more luminosity is the burst, either long or short. Okay, now let's try to understand if we can, putting together these ingredients, try to work out a minimal, let's say, model for describing these sources. I discovered that I cannot go back in my slides. I can just advance, so in case I will exit the presenter mode. Okay, so here I just want to make a very schematic description of what we think is working in these sources. We have different sources of energy. First of all, we have to start with the progenitors. Progenitors which can be in the form of an accreting object or a spinning, fast spinning magnetized object, which in any case are dealing with a source of energies which can be extracted through accretion, through rotation, and through magnetic field. And remember that this central engine are somehow the result of what was an original progenitor. So we can think about the ambient around them being polluted by matter. So we have at least three players. We have thermal energy, we have matter, and we have Poynting flux. So we have magnetic field. They can be present all together. In general, however, independently, let's say, from a naive, of course, description, independently from the one which is dominating, if any, we have that the evolution, in order to understand the physics of these sources, we have first to deal with the dynamical evolution of the of the outflow. So this, we can think about the fact that the central engine are able to produce a relativistic outflow, as we saw before, in which these three players are able to drive an acceleration phase, which is mainly opaque, so that basically the radiation is trapped within the expanding outflow. And during this phase, you have that most of the internal energy in any form is converted into kinetic energy. At some point, you have a dissipation event, which can be either the outflow becoming transparent, so having photospheric emission, or the development of instabilities that can lead to a formation of shocks, which are responsible for emitting photons. And here is where you produce the radiation. You can have channels which produce radiation directly through, for instance, photospheric emission or magnetic recognition. Magnetic recognition can also, let's say, produce part of the energy or pump part of the energy during the acceleration, which is then reconverted to kinetic energy. I don't want to go into the details of these equations. They are very simple, but it's a way of describing, let's say, the energy content of the outflow by separating the, let's say, thermal and matter energy content here, normalized to the mass energy, with respect to the magnetic field energy content, with these two parameters, eta and sigma. So that in general, the total energy content can be described by the combination of these two parameters here. And the subscript 0 means that we have somehow a certain amount of energy which is deposited at the base of the outflow, and during its evolution, basically during the acceleration, due to the fact that the internal energy is converted into kinetic energy, you have the appearance of this factor here, which is the bulk velocity, which is a function of the radius. The radius is the distance from the central engine, which basically evolves so that the gamma increases at the expense of the eta or sigma parameters decreasing. Now, depending on the amount, the relative amount of Poynting flux and thermal energy, you can have different configuration of the outflow. At the extremes, you have a purely magnetic field dominated outflow or a purely hot or fireball case. And in the following, I will concentrate on the purely, let's say, fireball hot outflow, where basically I will ignore the effects induced by the magnetic field in the outflow itself. Okay. So as I said, in order to understand the emission, we have first to understand the dynamics of these sources. The first part we deal with is starting from here. Now, when we look to a gamma reverse, we measure a certain luminosity, let's say 10 to the 52 Earth per second, okay? But this is, of course, the luminosity emitted in this phase here. So it's only a part. We can look to that as a lower limit, okay, or lower bound to the initial energy that was injected in the outflow. So in this equation, I want to just say that the observed luminosity is at least, or smaller in general, than the energy per unit time injected at the base of the outflow, which we can treat as a very simple black-body equation, from where it is possible to derive the temperature at the base of the outflow, which is of the order of few MeV. This is important because for typical parameters, this is telling that we are not far away from what we observe at least. So at least we are consistent with the peak of the prompt emission, which is around a few hundred keV or so. We can treat the acceleration as a totally opaque phase in which we have an adiabatic expansion, which is a relativistic adiabatic expansion. And by conserving the energy and the entropy, we can work out the scaling relation for the velocity of the outflow, which is the bulk velocity, and the temperature. So here and in the following, primed quantities mean quantities in the comoving frame, okay? And what you have is that by combining these two equations, you have that the bulk Lorentz factor increases as a function of radius from the central engine, while the comoving temperature decreases, basically. And this is represented in this plot here, where you have the scaling of the two basic macroscopic physical quantities. In general, this acceleration phase, or to make it simple, can last up to the point where all the internal energy has been converted to kinetic. There are, however, different other possibilities, but I choose this one to make it simple. And when this happens, of course, the let's say driving the source of energy which is driving the expansion is no more driving the expansion. So from a dynamical point of view, the outflow enter what is called the coasting phase, where it basically coasts with constant velocity, which is represented by this red horizontal line here. And in this phase, what is possible is that due to the expansion of the source, the optical depth, which was basically dominated by different source of opacity, but at these distances is basically dominated by electron scattering, can become lower than 1, and so that the photons can be released. This is what we call the photospheric radius, which can be derived and put into relation with the observable of the source, so the luminosity and the Bell-Currents factor. And for typical values, it is of the order of 10 to the 12 centimeter. This is, let's say, could be regarded as the first light from the outflow. And if this happens, and should happen from at least within this model, the emission that we should see is a kind of a thermal like emission. However, if you now think about the let's say injection of energy by the central engine as a discrete process, you might think about the fact that during the coasting phase you have discretized part of the outflow which are moving with slightly different values of their Bell-Currents factor. If this happens, you can create a condition in which different parts of the outflow collide one with the other, producing a shock. In this very simplified view, what I'm thinking about is two, let's say, blobs or two shells. Imagine that as you like. But the key point is that they are, let's say, in a ordering of their velocity, so that the rear shell is moving faster than the front one in order to collide. And by basic ballistic argument, assuming that they are separated by a distance which is proportional to their variability time scale, when they collide, they develop a shock. You can derive the radius when this happens, which is slightly larger for typical values than the radius where photospheric emission happens. The dissipation, so both the photospheric emission, but more importantly, the internal shocks, which are the collision between in this simplified model between two shells, but of course can be an n-body interaction, is a tool in order to reconvert the kinetic energy that was acquired during the acceleration into radiation. And we will see in a moment what kind of radiation. Just to, yes.
Can we just stop a second? There are a couple of questions in the chat.
Yes, thank you. So because I don't know if I'm not using properly Zoom, but I cannot see the list of so I cannot see the Zoom controller. So good if you
don't you focus on your lecture. We take care of this, okay? And okay, I'm interrupting basically when you're changing slides so that you don't interrupt the flow. But there were a question by Constantin. Constantin, do you want to?
Sure. A couple of slides back, you showed some gamma ray bursts as a function of redshift. And I was wondering how you extract the redshift. Because if I guess you take a spectrum.
Yes, definitely. So sorry, I didn't go into the detail. The redshift is measured by taking the spectrum whenever you, now it's done, I would say quite often, whenever you well localize the source in the optical counterpart, so that you can take a spectrum, and by matching the lines, you can, at least a few lines, you can derive the redshift. This is, of course, depends on the instrument you use, on the frequency and on the distance of the source. For, let's say, in this distribution, if you want, the curiosity is that up to redshift 5, most of the redshifts are spectroscopic redshifts derived with high resolution optical spectra. At larger redshift, the technique that, for instance, allowed to measure the redshift for the burst here at redshift 8.2, which is GRB, don't remember the name of 5 something. That technique is using the Lyman alpha dropout in a kind of a broadband spectrum rather than a high resolution, a medium resolution spectrum.
Okay, and how can you be, because if I understood correctly, your matter is moving relativistically. So how do you make sure that the lines are not shifted due to some relativistic effect?
Well, because first of all, when you go to measure the redshift of the afterglow, the relativistic effect are much reduced because the outflow is decelerating, okay? And secondly, because this effect is minimal with respect to the cosmological one, okay? And you can correct for that as well but you I mean, it's affecting all the spectrum systematically.
Okay, thank you.
There is another question from Chiara. Chiara, do you want to speak up?
Yes, sorry, since I have a question at this particular slide. So you talked about a selection effect here in the redshift distribution. Can you clarify, because I couldn't follow?
Yes, sorry. So I was quite fast. You can see there are, first of all, selection effect here, which is very common studying cosmological sources, because if you have an instrument, this is not really the case here because these points are collected by different instruments. But if you have an instrument with a limiting flux, this translates into a kind of square dependence with the distance, with the luminosity distance, cut, which is somewhere down here. And so the selection effect is that at low redshift, you basically more frequently see dim events, and at high redshift or low energy events, at high redshift, you naturally select, because of the selection bias, the most energetic events, okay? Because the dim ones are below the selection effect. There are other selection effects related to the fact that at low redshift, you are sampling a relatively small volume of the universe. So since the luminosity or energy distribution of the sources is a steep power law, you are going to pick up more frequently the low energy events rather than the high energy one, because of a volume, let's say, limiting amount, size of the volume that you sample. Whereas at high redshift, of course, you have a larger volume of the sampling universe. On the redshift distribution, this affects the fact that what you see, let's say the combination, let's say, of the limiting flux of the instrument and many other selection effects, which are very difficult to treat, in the sense that in order to measure a redshift, there are selection effects which are, let's say, more human-based. You need to have an approved proposal with at a telescope which is of the 10-meter size. You need the source to be observable in nighttime. The weather should be good. And so, I mean, the shape in general can be affected of the redshift distribution. The observed one can be affected by a combination of selection effects. But despite the last one I discussed are difficult to account for, one possible way is, which is not this plot here, is to extract a complete sample of sources, which if cut at high fluxes is typically also complete in redshift. And with that, you can get rid of the selection bias or account for the selection bias. And for instance, what typically is done in astronomy is to reconstruct the luminosity function and the intrinsic redshift distribution of the sources. Okay. Did I answer your question?
Yes, yes. Just another thing though that confuses me. So, but because from the previous slides, it didn't seem to me, at least, that the longer GRBs would have a more energetic distribution, a more energetic emission than the short ones.
From this one, you mean?
From this one and also from the one with the spectrum.
This one. No, for this. Okay, this one.
Yeah, for example.
Okay, no. So this is a sketch here. It's like this is the observer frame flux. Okay, observer frame nu spectrum versus the energy, and this is just to show that they have a similar peak energy, and it is a comparison of the energetic of the spectral energy distribution. Let's say that the energy is coming from the integral of this curve here, provided that you multiply by the square of the luminosity distance, which from the next slide, you see it's quite different. So it turns out that the integral of the red is smaller on average, smaller luminosity, smaller energy than the integral of the blue, because the blue GLBs are at redshift 2 and the short ones are on average at redshift 0.5.
Okay, thank you very much.
Okay. Sorry, I forgot to say this is observer frame, and it's just a sketch just to show the difference of the two populations in general as a take-home message.
And Pierre, you had this question about the R naught on the last slide we were looking at.
This one. This one. No, this one I was probably. Okay.
Right.
Yes,
yeah.
Just how you know R naught here, because if you want to know T naught, right, and you measure the luminosity, you need to know R naught, right?
R naught. You mean here?
Well, we don't see your pointer, but
yet again, we don't hear ER.
Okay. So, sorry. You mean this value here?
Yes.
Okay. No. This is just a scaling relation where R naught can be thought as being the base of the jet, or a size which is proportional to the, let's say, size of the central object. So you can think about something scaling with the last stable orbit of a black hole, or radius of the neutron star, but it's just for reference. Okay, when you it's just to understand the physics. I mean, it's not used directly for the for the observation. It's quite difficult to derive this value. It is possible when for instance, you clearly detect the photospheric emission, because in that case you can draw back the let's say evolution, assuming of course this model is valid, or other, you can draw back and estimate the value of R naught. The interesting point is that let's say I said half of the story, but if instead of converting all the energy into kinetic, let's say for some reasons the transparency happens before the end of the acceleration, of course you stop the acceleration there and you release a large amount of internal energy in terms of photons. You should see a bright photosphere emission, and the temperature, if you combine this equation, you see that the temperature you measure of the black body in that case is equal to the initial one, because the effects here cancel out because of the mutual inverse dependence, or the similar dependence of the temperature, moving frame, and gamma from the radius.
Are there any other questions since we are taking a quick pause here in the lecture? No? Okay, so I think we can move forward.
Okay. May I ask you, Eric, what is the timing? So
right. So the nominal, I think what we usually do is to stop at 12:30. And there is a half hour here that is for question, and maybe if you wish, we can break. I think it's a good thing that we take a quick break at some point.
Okay.
But it depends on, it depends on how on your lecture. Maybe there is a good point. There is a good
Well, let's say that I structured this first lecture into two parts. I'm still in the first one. Probably I should skip some slides or boost a bit, because I would like to finish with the prompt emission, let's say description and understanding. And then I have the second part, which is about the afterglow. So if you want, I don't know. So I understood we have still 1 hour.
We still have 1 hour and 20 minutes.
Okay. So we could, if you can wait, if it is okay for everybody, I can go on until the end of the prompt, and then we take a small break and we enter the afterglow, and then I'm done.
I think that's okay.
Okay, thank you. So this slide is basically the same as before. I just wanted to show you that so there are two possible emission components during the prompt. One is the one at the photosphere, and the other one is through the shocks. They are quite different because in terms of spectral shape, at the photosphere, we should expect a thermal or quasi-thermal black body, whereas in the shocks, we have that these are places where you can accelerate the particles, you can you have a large magnetic field that slightly can be amplified, so the emission that comes out is non-thermal, probably synchrotron, and one key point is that by thinking about the development of shocks as due to the instability, discretization of the, for instance, injection of energy at the base of the outflow, this can also account for the fast variability, because you can imagine individual shocks producing spikes and several bunch of shocks producing pulses and so forth. Let's say that these two emission components are in general have been observed, but the evidence for thermal components is much less frequent than non-thermal emission. Okay, just a few words how the emission happens at the shock. So the game here is to deal with let's say the part of the energy distribution of the particles which pertains to the very high energies. There are different ways of describing the shocks. Here you see a slide that tries to make the point, the present point about what we know about acceleration of particles at the shock. This is a simulation of particle in cell simulations of an unmagnetized relativistic collision shocks, where you have typically that this simulation showed the development of an energy distribution of the particles, which is made up of a broad thermal Maxwellian-like component and a high energy tail, probably with a cutoff. The key point here is that this simulation indicates that typically the power law slope is with a value which is 2.4. It can extend 10 times at larger energies with respect to the peak of the Maxwellian, and it can contain roughly 10% or a few more of the energy in a non-thermal tail. What we need to interpret the prompt emission is basically the fact that we can think about electrons accelerated into a non-thermal tail with a value of P describing the slope of this power law. Now, if we think about schematically describing the shock as the encounter of these two shells, we have a region in which basically you have the enhancement of the density and the exchange of energy into the particles and magnetic field. A possible way of understanding this simply is to take a reference frame in the shock and look into the material which is in the upstream coming towards the shock. And the bulk of this material is in the form of its basically kinetic energy, where gamma s now is the velocity of the shock, which is, let's say, a factor, about 1.4, the relative value of the Bulk-Lorentz factor of the two colliding shells here. Okay, these are details, but they can be derived simply from energy momentum conservation. The key point is that the electrons which are accelerated behind the shock, so in the downstream region, get a fraction of the energy of the upstream protons. And since the description of the shocks either can be done with complicated details of simulations of the shock, or in a very simplified way, this is what is done in GRB's physics, by simply assuming that a fraction epsilon E of the upstream flow is shared with the electrons. By taking this equation, you end up with the typical energy of the accelerated electrons, with which for typical values is of the order of 10 to the 4, 10 to the 5. The other important ingredient to have synchrotron emission is the magnetic field, which again is computed by taking the Poynting flux luminosity equal to a fraction of the luminosity of the outflow, which is in front of the shock. And this is through this parameter epsilon b, from which it is possible to derive the comoving frame magnetic field in the post-shock region, which for typical values is of the order of 10 to the 6. Now, we have all the ingredients to understand the prompt emission, synchrotron prompt emission, because the first thing we have to ask ourselves is the particles which are accelerated into this non-thermal tail, gamma to the minus p, they cool through synchrotron emission. And the cooling time scale, so how fast they emit, is basically derived by taking the particle energy divided by the synchrotron power. This allows us to compute the cooling time scale, which for typical values is much smaller than dynamical time scale. The dynamical time scale can be thought about at the time over which the outflow doubles its radius or so. So it's related to the expansion. This condition is called fast cooling, and from a physical point of view, it means that the injected power law of the electrons in a very short time scale, cooling time scale, softens. So most of the electrons cool down. It's depleted of electrons. It takes a value which, by solving the continuity equation, becomes gamma to the minus p minus 1, and it builds up a low energy part, which is gamma to the minus 2. So over a time scale which can be of the order of 10 to the minus 6 seconds, you have from an injected power law something which becomes a broken power law like this, where you have two characteristic energies, the minimum energy of the injected electrons and the cooling energy, where most of the electrons go because of losing their energies. By taking the synchrotron equations, which basically relate the energy of the electrons with the frequency, you can pass from the injected energy distribution to the spectrum. And the spectrum that comes up is made, at least for what concerns the prompt emission and the energy range covered by the prompt emission, of these three power laws, where you have the high energy part of the spectrum, which, as you can see from the colors, is related to the cooled energy distribution of the electrons. The intermediate part is the part related to the cooling part of the energy distribution of the electrons, nu to the minus 1/2, and this part is the single synchrotron electron shape, where you have, as you can see, the correspondence between the characteristic energies of the electrons and the characteristic frequency of the synchrotron spectrum. Okay, I leave this for you to check if I did it correctly, but by taking the synchrotron equations, you can also verify that for typical values, the peak of this emission, which this is the flux, if you multiply by the frequency, you get the nu f nu, and it peaks at nu m. So the peak of this spectrum is for typical values of the order of a few tens or hundreds of keV, which is consistent with the observation. So synchrotron emission seems to be the leading process producing the emission in GRBs, but here I propose you a problem, because now I go back to the example of the spectrum I showed you at the beginning, which is guiding our understanding. And here, okay, if I now interpret this emission spectrum of the prompt phase, this is valid for both long and short GRBs. Even what I'm saying, even more dramatic for short, you will understand in a moment. So if I take this spectrum and I compare it with the argument we just made for the synchrotron, I see that I can interpret the high energy part of the spectrum as related, let's say, to the p-value, so to the injected slope, to the slope of the injected, to the slope of the injected electrons, okay, which is here. So this part, I represent it with the shaded region because its, let's say, value can somehow vary if you just allow some varying values for the P. The problem is that synchrotron emission predicts that the low energy part of the spectrum, okay, this part here is fixed. It should be e to the minus frequency to the minus 3/2 in photon, or frequency to the 1/2 in nu f nu. And as you can see already from this example, the spectrum is harder. You can believe this by taking this plot here, which represents not a single burst, but a sample of both long and short GRBs. Here are represented as a function of their duration. So blue are long and red are short. And this is the photon energy characterizing the low energy part of the spectrum, compared with the value expected for synchrotron emission in cooling regime, which is this value here. You see that basically the majority of long GRBs and all short GRBs are inconsistent with this limit. So this argument represented for years the fact that we seem to have a problem in interpreting the prompt emission of GRBs as synchrotron. Possible solutions, there are many, and I think one of those, for instance, by properly computing a bit more complicated synchrotron emission, considering inverse Compton, like in the paper by Dane and collaborators, or by relying again on the observations, since recent studies, I will be very brief here, seems to show that by an analysis which extends to very low energy, at least for the brightest burst, the spectrum is not that much inconsistent with synchrotron. And there is the appearance of a break at low energy, which can be interpreted as the cooling break. So sorry, I go back here. So it seems to have this shape, at least for a fraction of GRBs. This is the maximum frequency, nu m, corresponding to the minimum injected electron energy. This is the cooling frequency, corresponding to the energy where electrons cool. And the slopes below the cooling frequency and above the cooling frequency are roughly consistent with the synchrotron slopes. These are some of the papers that made these studies. And well, I would say that after years, there seems to be a kind of we see the end of the tunnel in interpreting the synchrotron prompt emission, even though this interpretation is not completely closed. There are still some problems. So I think I can stop here. If there are questions on this first part, I can take it now, and then we can have the break, and then we resume and go to the afterglow. So I just want to say something. I'm sorry, probably I was a bit fast on some slides, but I tried to make them self-explicative, and I hope if something was not clear, you can go back and take a calm look to the slides individually.
I agree. Well, not that you went fast. I think we'll have time for question, and people will perhaps elaborate further once they have digested. Maybe what you could point the student to is there are probably reviews on which they can have a global and a text that would go through in the material you presented. Maybe you can think of it and include those references to your slide.
I made a list in the very few first slides.
Okay, very good.
They were indeed mainly review related to the multi-messenger probably, but there are also a couple of reviews for the prompt which are valid and recent. I can add to the slides so that, yeah, good idea. Thank you.
So let's take just a minute to see whether there are questions on the prompt emission part. Yes, there is a hand up by Chiara.
Sorry, so I'm not sure I followed properly. So the point is, so you thought for a while that the prediction of the synchrotron emission was not adapted, but then there are new observations that shows that actually it is not so bad.
Yes, in general,
the bottom
perfect.
Line.
Yes, in general, yes. The only thing is that we thought for more than a while, I think we thought for nearly 40 years that synchrotron had major problems. Recently, both from a theoretical point of view and from the observational one, I think there were major advances in, let's say, reconciling the theory, which is the expectation is synchrotron because you have relativistic shock, you have shocks, you have relativistic particles, you have a strong magnetic field, so it's quite unavoidable with the observed spectra. The story why this happened so late, it's a long one. It's not completely new. It's not due to the fact that we acquired new observation. It's, I would say, more a way of looking to the observations from a different perspective. Basically, in this specific case I'm showing here, this spectrum was, this as many others, like the one that I was showing before, was typically fitted with a single break. So a model which you know, goes up with a single power law, more or less here, and then goes down. And of course, in this case, the fit would be rejected because of statistical argument. But for the majority of other bursts, which are dimmer, it would be an acceptable fit. And this prevented the, let's say, evidence of the discovery of the evidence of the fact that indeed the spectrum is slightly different. And so when people started to fit the spectrum with two breaks, okay, it appeared that at least in the brightest burst where you have enough statistic, these two breaks are present. And this is a first step towards the, let's say, having a shape similar to the synchrotron one. This is half of the story because in reality, if it were synchrotron, as I described it before, the cooling time scale is so fast that this break here should be out of the window, basically, because electrons would cool down basically to gamma equal 1. They lose all the energy. So while this opens a possibility to interpret this spectrum as others as synchrotron emission, it opens another question. Because in order to have the cooling frequency at 100 keV, you need to let the particles which are emitting to cool, but not so much. So the interpretation is that this emission is synchrotron, but synchrotron in a regime which is cooling, but only moderate. It's called indeed moderate fast cooling regime. So it's a bit more complicated. I wanted just to give you a flavor, I hope, but you catch perfectly the, let's say, the problem and the issue. The fact is that we have been dealing with this issue for quite a long time, and now we are trying to give an interpretation of these in light of these new results, which, however, open other problems.
And if I may, so the part of the spectrum at high energy, for this one, you don't really need a model. It is the energy which is injected.
Well, for the high energy, you can think about, for instance, in this specific burst, in this reference, you find also the discussion. The slope of the high energy, if you interpret the emission as synchrotron, can give you the value of P of the injected electrons, okay? In this specific case, for instance, the value of P that we derived, that was derived is quite steep, which is another problem because it is saying that the acceleration of particles at the shock, in this case at least, must be not that much efficient as the one that I described with as coming out from hydrodynamical simulations. But yes, the information you can get from this part are on the, let's say, shape of the injected energy distribution of the particles. And in general, this does not represent a problem, as I told you, because you can have some allowance in the slope related to the fact that you can have some allowance, not that much, in the slope of the accelerated particles. What happens is that if you go to higher energies, at some point, the argument we discussed at the beginning, so the gamma-gamma opacity can, however, start to, let's say, play a role in deploying the spectrum from photons. So at higher energies and in some bursts also at energies consistent with this value, so you can have a further break due to internal absorption.
Okay, thank you very much. It's clear.
Thank you. Thank you.
Any other question for Giancarlo?
Can I ask one question quick?
Sure.
So mostly the discussion is based on the single shock. If you considering the multiple shock interaction, will that scenario be more complicated or in general consistent with your your description so far?
This is a good question. So I choose just to present the single shock because it can be regarded as a brick to understand at least what is happening. In general, a correct description should be that of developing multiple shocks or developing a shock in which energy can be injected by the arrival of other shells. But what really happens is, I think, not fully understood. I mean, the advantage of having multiple shocks is that you can at least, from a, let's say, very general point of view, account for the fast variability. The detailed description of the shocks becomes very difficult. There are numerical simulations that describe it. The complication is that, of course, you have to deal with the dynamics and with the unknown processes, or let's say, a variability of the injection of the energy at the base, which, for instance, if the system, the central system, the central engine is an accreting black hole, maybe could be related to the, let's say, fragmentation of the accretion disk or intermittent accretion related to some other phenomenon. And so it becomes very much complicated, and it's, I would say, purely theoretical. I mean, what we only see in these sources, or the first light we see, is the prompt emission. And from that, we have to, let's say, extrapolate backward with purely theoretical arguments to understand what is happening. And what is happening is what makes light appear as it is. So yes, in general, it's possible, and it has been done. Of course, it's subject to assumptions and difficult to test, I would say.
Yeah, thank you very much.
I'm also telling half of the story, as I said, because you can have model, which is the magnetic model, in which all the features I described can have a different, let's say, a similar phenomenology, but a different physical origin.
Yeah, thank you.
I think we should take this break. But before we do this, let's try to do this group photo, okay? So I'd like to ask you, I mean, the one that wants to be on the photo to open their video. I can see 25 participants at a time now. When you know, we'll be ready, I will take 3 shots, and we'll collect this into a mosaic.
Sorry, Rick, should I stop the streaming of the video?
No, it's okay. It's okay. I think I reduced this on the side so that I can see all the faces. And well, feel free not to switch on your video if you don't want to. I mean, that's perfectly fine. We don't want to force people there. So very nice. I see many faces there. Okay, get ready. So cheese. Take one. Okay. me take another one. All right. And the last one. Thank you very much. Okay, so I think we take a break for 5 minutes. What do you say, Giancarlo? Is that okay?
Okay.
So we'll reconvene at 11:40 for me, 42. Okay? Talk to you in a few minutes. Okay. Are we okay to resume the lecture? I guess we are. So, Carlo, whenever you.
Okay, so I can. So we restart after describing the prompt and understanding, let's say, the basics. I will try to do the same with the afterglow emission. Again, I try to make a selection of the properties, and I will try to give you a very general physical idea, I hope clear enough, which can be useful when you know, studying the electromagnetic emission of future gravitational wave events. And let's say the description I will give in the first part of the afterglow is of GRBs in general, of course, much different from the one we saw in 1708-17. In the end, I will try to clarify what are the orientation effects. And of course, tomorrow we will describe the source. And of course, I hope some of the concepts described today will be useful. Now, as for the prompt emission, I could spend the rest of the lecture describing all the different features we have and the diversity we have in the afterglow, which is not useful, I think. So I just show you an example of an afterglow of a GRB. This is a quite extraordinary case because it's one of the most energetic events ever detected. It is at redshift 0.34. And you see here the two, let's say, basic ways of looking to the afterglow emission in terms of light curve here. So flux density as a function of time at different, in different energy bands. What you see is that the afterglow emission is very long, is detected in this case up to 100 days, and it's distributed over all the frequencies. Of course, the relative position of this light curve is obtained by scaling by the factors that you see written in parentheses for some of them. But as you can see, it is detected, this event. Sorry, this is the drawback of being at home. I will not answer, probably is Amazon. And you see that the drawback of this kind of, no, the drawback, sorry, the drawback is the ringing of the bell. But now what I wanted to say is that this burst is exceptional because it was detected from the very high energy to the radio band, okay? So you see the very high energy emission is this one detected by LAT at GeV. This is the, let's say, MEV KV energy emission detected by BAT on board Swift. This is the X-ray telescope on board Swift in the 0.210 KV. These are optical UV light curves. Then you go in the infrared here and then to the radio band. On this other side, you see the spectrum represented over different time, okay? And the main point you should see is that, of course, the spectrum reflects, or vice versa, the light curve reflects the spectrum, but you can think about the link about these two as like being on the banks of a river, okay? So if you imagine that you have an instrument that samples a given frequency, for instance, this one, the light curve you see is the reflection of the fact that the spectrum evolves with time, okay? And as you can see in this particular case, there is a general shifting and softening at some point of the spectrum as a function of time towards the very low energies. And this is why, if you want the emission, when you look to a typical gamma ray burst, let's say it becomes brighter as time goes by at lower frequencies progressively, with the radio band being that one, which due also to the extremely high sensitivity of radio interferometers and a large radio telescope, can be followed and studied up to really very late times. Bottom line is that we can understand or try to understand the afterglow emission just by thinking as an evolution in the frequency and time domain described, at least in this example, but there are much more complicated cases, as power laws. So where you have let's say the spectrum is described by a power law in the frequency and the light curve as a power law decaying as a function of time. So this is an example, as I said. I'm very sorry. I wanted to give you a general picture of the afterglow emission. So I tried to make a kind of a summary, which probably is not complete. I hope it's clear enough. If not, apologize for this, which is represented in this plot here. So here I'm just showing all the possible features and how complicated an afterglow of a GRB can be. Of course, what I'm showing here not necessarily is present in each afterglow of a gamma ray burst, but just part of it, because the example I showed you before is also one of the best sampled GRBs ever, both in time and frequency. But in general, we can describe, let's say, through this scheme, how the afterglow is, let's say, the properties of the afterglow emission as a function of time, at least in the X-ray, optical, and radio band. We can identify at least 4 phases. The prompt one, which indeed is coincident with the prompt phase, where sometimes the afterglow typically is very dim. When it is detected in the optical, it is typically rising, or it has a bright flare. The bright flare is due to the reverse shock, because I will tell you in a moment, the afterglow emission is produced by the shock developed by the expansion of the outflow in the interstellar medium, which decelerates it. And there is the development, as in every shock, of a forward shock, which is expanding into the external medium, and the reverse one, which is expanding into the outflow itself. This emission sometimes pops up in the optical band. Also in the X-ray, there is, let's say, during the prompt, a connection with the prompt emission itself. In the very early phases, which approximately goes from 100 seconds to a few hours, you have, as you see, different behaviors according to the band where you look to the afterglow emission. In the optical band, you have a decay, so you have typically a rising phase, and it happens to show a peak, which is called the onset of the afterglow. In the X-ray, typically you have a steep decay, followed by a nearly constant luminosity phase, which is called plateau. In the X-rays, in this phase, you can also have the superposition of bright flares, whose origin is somehow possibly related to late time activities of the central engine. After this early phase, the afterglow undergoes an intermediate phase where typically the evolution of the X-ray light curve and of the optical light curve is much more similar. And in this phase, for instance, in short GRBs, if bright enough and if orientation effects cooperate, you can have the detection of the kilonova, which indeed, okay, then we have the different time scale related to the color, and which is indeed related to the orientation, but I would give as a rough estimate time scales between hours and 1 week, more or less. The end of this intermediate phase is, when observed, signed by a steepening of the afterglow emission, which is interpreted as the evidence, observational evidence of the fact that GRBs are not isotropic, but they do have a jet. This is called jet break. The steepening, when observed, not always, and in the best cases, is achromatic, because it's, we will see later, a dynamical effect, dynamical and relativistic effect combined. And in this late phase, what happens is that typically the radio emission is seen rising and then decaying. The rise and decay of the radio emission is related to the fact in the radio band at very early times, the spectrum is strongly absorbed, self-absorbed, and you have to wait for the expansion of the source of the emitting region in order to have the transition from thick to thin. In these very late phases, for long GRBs, it is possible also to observe on time scale of larger than 2 weeks, approximately, the supernova, which pops up as a kind of a bump in the light curve. So again, this is an oversimplified scheme, but which summarizes, let's say, the main features. Probably I forgot something because I wanted, or I didn't show everything. What I will try now to describe in more details, which I think are relevant because they can allow us to understand a bit the physics of the afterglow, is the origin of the onset and the jet break, okay? And then from the jet break, we will enter on in the realm of having the jet and moving it with different orientation with respect to the line of sight and see what happens. So I go back to the scheme we followed before. And so the next piece of information is that after the radiation producing the prompt emission, we have this phase, which is the deceleration phase. The deceleration basically arises from the fact that the outflow is expanding into the interstellar medium and is shocking the interstellar medium. So you can naively think that it is decelerated because of the, let's say, increase in a way of its mass which decreases the velocity. The scaling relation, which let's say it's that of a relativistic blast wave, can be simply derived by equating the energy, internal energy of the blast wave, which is E, to the relativistic energy of the interstellar medium, where in the term rho we encode the property of the interstellar medium. In the case of an interstellar medium with a constant density, you work out that since the expansion of the outflow is adiabatic, you have that gamma scales as the radius. So radius is the distance from the central engine, again as before, to the -3/2. And by taking the relation between time and radius, this corresponds to decay as a function of time to the -3/8. I want to just make a notice about the fact that this is valid if the density around the burst is constant. And I would say that this kind of assumption we can think is valid in general for short GRBs. Instead, if from a theoretical point of view, in the case of long gamma ray bursts, we expect that the external medium has let's say, a density which decays as a function of the distance from the source, because of the fact that before the formation of the central engine, therefore before the core collapse of the progenitor, the star, the massive star, probably shed around a fraction of its mass through winds and shaped in a way the density around in the surrounding with a decaying density. This is expected from theoretical point of view, I would say hardly confirmed by observations, but in some cases, yes. And the scaling is different with respect to the one I'm showing here. So you can think that this scaling is, from a theoretical point of view and also observational one, more often valid for short GRBs. Now, the interesting point is that now we have the complete description, at least up to relatively late times, of the dynamical evolution of the outflow. And since this is an important point, because you see that the outflow after the prompt emission starts decelerating, and so you have the transition from the constant to the decaying gamma factor evolution. This point is a relevant point because it corresponds in the light curve to a peak. The simple argument to understand this is the following. So if you think about the luminosity that you as an observer see, think about the outflow coming towards you. This is a factor gamma squared times the intrinsic luminosity. And you can think that the intrinsic luminosity, intrinsic means co-moving one here, is prime, is proportional to the, let's say, size or radius of the expanding source. Think about a kind of a spherical explosion, okay? Now, this equation here, if you think about before starting to decelerate, reduces just to the dependence on the radius, because gamma is constant during the coasting phase. Whereas during the decaying, the decelerating phase, the luminosity scales as the radius to the -1. And so transforming into time, what you get is that the luminosity, so the light curve, this is valid for the bolometric luminosity, should increase, peak, and decrease. Well met, this prediction, by the observation. Here you see an historical GRB dating back to 2006, where in the optical band, a clear peak is detected, and this peak is at about 130 seconds. And by basically taking the dynamical evolution and the basic energy conservation equation, you can work out what is the value of the outflow before starting the deceleration. So you end up estimating the bulk Lorentz factor at the maximum of its dynamical evolution. So after the acceleration, when it is constant, and it is indicated by gamma naught, okay? It's not the initial one, it's the maximum one, okay, that you get. And for this specific case, you have that the time corresponds, given the energy of the burst and the density, the parameters are the energy, the density, and the deceleration time. Of course, you need to know the redshift, but it's a factor of a few in this kind of calculation. You get that gamma 0 in this case is of the order of 400. So this is, if you want, even though model dependent, another evidence that indeed the outflow is relativistic. What is nice is that whenever you can measure this peak, if you interpret that as the deceleration peak, okay, due to this argument, very simple one, you can infer a fundamental physical property of the burst, okay? And this is important because by collecting a number of GRBs which show this peak, and okay, with some, how to say, being careful in interpreting correctly this peak as due to deceleration and not other effects, which could make the peak appear even not due to deceleration, but okay, trust me, what you see is that bursts which show the peak, for which you can derive the value of the gamma, are represented by the red and green points here, and the other are upper and lower limits. And the result is that there is a quite strong correlation between the bulk Lorentz factor, so let's say the velocity, the dynamics, and the luminosity of the source. And similarly between the bulk Lorentz factor and the peak energy. Now, if you recall what we did, what we said that this is the bulk Lorentz factor during the coasting phase, I say it again. And the scaling relations are more or less like this. So if you recall the correlation we described at the beginning, the one involving the prompt emission properties, so the peak energy of the FNU spectrum and the luminosity or isotropic energy, what you see is that by combining these two equations, which relate the prompt emission properties to the dynamics, you end up with the correlations that empirical one you get by observing the spectrum and measuring the energy when you have measured the redshift, for the argument we did before. For the bottom line, I think here is that apparently what we have from these observations is that the larger is the luminosity or energy and the faster is the outflow. So the faster, the brighter. Now, let me try to explain a bit about the external shock, or which is which is producing the afterglow emission. It's very much similar, the treatment, to the internal shock treatment, with the difference that internal shock is something which is happening between, let's say, cold material. The two shells are indeed bearing internal energy themselves. In this case, hot material. In this case, instead, part of the material, which is the interstellar medium, is relatively cold, let's say. And this, let's say, introduces some slight differences in the very basic treatment that we are using. But the equations are more or less the same. So this one is similar to the one we used before. This gives you, let's say, by assuming that part of the shock energy goes into the accelerated particles, allows you to derive the typical energy of the accelerated electrons. The second equation gives you the magnetic field. So the magnetic field energy density here is equal to the post-shock accelerated energy of the particles in this region here between the forward and the reverse shock. The third equation is the cooling time scale, similar to the one, is the one that we derived before. So the energy of the emitting particles divided by the synchrotron power. If you just take from this apparently complicated equation, and gamma is the gamma of the forward shock in this treatment. If you just ignore the constant and you just take the basic scaling with the Bell-Currents factor or time or magnetic field, you end up with the set of these three equations. And now from the first one and the third one, you can transform, like what we did for the prompt emission, the energy of the electrons, so the injected energy, the energy of the injected electrons, the minimum energy of the power law, and the cooling energy, where they cool, into the corresponding frequencies. The difference with respect to the prompt emission is that while in the prompt we were in fast cooling regime, in the afterglow emission, not immediately, but at some point, we can think about the emission being in slow cooling regime. So you see that basically the frequencies these two frequencies are interchanged. The reason being the fact that the expansion and let's say loss of energy due to the adiabatic expansion counterbalance the cooling of the particles accelerated by the shock. The point is that what is interesting is that by deriving this scaling relation, you have that the characteristic frequency, which is the maximum in the nu representation, and the cooling frequency evolve differently as a function of time towards lower energies. This is valid for the case of a constant interstellar medium density, okay? And in this case, I don't have time to show you, but trust me, the synchrotron self-absorption energy, which we didn't, frequency, which we didn't care about before, now it's fixed, doesn't move. So the flux at the peak of the emission depends on the number density of particles and on the power of synchrotron emission of each emitting particle. And if you just use the scaling and you plug in the equations that are represented here, you end up with a scaling relation which is constant with time. This is to, let's say, convince you that during the afterglow evolution, due to the dynamics and the link that we can establish with very simple consideration between the dynamics and the radiation, radiative process at the shock, what we have is that we can understand that at a given point and successive point, as if you take snapshot or pictures of the afterglow spectrum as a function of time, you should see this spectrum moving at lower energies, with these frequencies, so the cooling and the maximum frequency moving differently, and the peak of the spectrum remaining almost constant as a function of time. So it's not really a rigid translation, because there is also the change in the extension or separation of these two frequencies. I try to make this with an example. So at a given time subsequent to the one corresponding to this, let's say, ideal picture of the spectrum could appear, for instance, like this, where you see there was a slight translation of the cooling frequency, a major movement of the maximum frequency, more or less the peak of the spectrum is constant, and there is a reduction of the nu to the 1/3 part of the spectrum. The self-absorption frequency is fixed. Now, if you make the exercise of being on the bank of the river and choosing your favorite, let's say, frequency or sampling frequency of your instrument, you can understand that this temporal evolution of the emission, which is indeed induced by basically the dynamic evolution of the deceleration, is responsible for the behavior of the light curve that we see in the afterglow. I try to make this clear here, at least, let's say, for the intermediate and late phases. If you think about sampling at an energy which is more or less in this region here, you should see a decay of the emission. If the X-ray is sampling also this energy part, you see a parallel evolution, okay, up to the jet break. And as you see, understanding this, At some point, the sampling of the radio band is just increasing because you have, where is it? You have, as you see, the increase of the flux up to the point in which this frequency comes here and then evolves at lower frequency, and then you see the radio band also decreasing. I think that if you have never thought about this, probably the first time is a bit difficult. I encourage you to do your own movie or your own sketch, and it becomes really, really simple to understand. And I hope I made it clear enough with this sketch. I want to open a parenthesis if there are no questions up to now, which is really a parenthesis, but I think it's worth mentioning. So can I proceed, or do you have any?
I don't see any question. Let me make a call here. Are there any questions on this initial part on afterglow? No, I don't see any hand up.
Okay, the parenthesis I want to open is related to the fact that in the field of GRBs, of course, apart from the opening of the fantastic multi-messenger window, there was another window which maybe is more interesting for experts, but I think it's very promising, which is the very high energy window. I mentioned that at the beginning with the summary slide of the fundamental steps forward. And it is represented here. Probably you are aware of the fact that in January 19, the MAGIC collaboration detected the very high energy emission of this event. So here you see an SED, so a spectrum, where you see the MEV typical peaked synchrotron spectrum, the one I've been describing so far for the prompt and for this is for the, let's say for the MEV component as detected from XRT, GBM, and BAT. Starting 68 seconds after the trigger up to almost nearly 1 hour, there was the detection of this emission component here, which in the MAGIC energy range is observed as a decaying power law. Thanks to the presence of LAT on board Fermi in the intermediate region, let's say that the general shape of the spectrum seems to be that of the double hump. This is the evidence of the fact that, as expected, and indeed in my treatment, I didn't mention it, but it's present in all the calculation I did, of course, there can be the inverse Compton component of the emission. And in particular, this component that we typically think about in GRBs is the so-called synchrotron self-Compton component, meaning that the accelerated electrons at the shock are responsible both for the emission of the synchrotron photons and for their, let's say, Compton boost at higher energy. So they do both, they have a double role in this. Now, why this is important? Because, let's say, very simplifying the situation, there is a relation with between these two peaks, which is related to physical quantities, like, for instance, the typical energy of the electrons. The interpretation, therefore, of this second peak as a synchrotron self-Compton emission places a limit on the energy of the electrons, which in this case is relatively small. And this is an issue which has been discussed in the literature, probably is not completely solved, and probably will be solved with the study of many of these sources. I just wanted to mention this because this is a recently born, let's say, a field, not field, but the opening of this window is very recent, but I think it's very promising because it's another way or a complementary way to access the physics of the emission region and the acceleration of the particles themselves. And by the way, it also is the highest energy part of the emission, which could have connections with the other messengers. So the presence of the possibility that GRBs can be accelerators of ultra-high energy cosmic rays and eventually producers of neutrinos. I close the parenthesis. And we go back to the, say, normal GRB. So far, what I've been describing, if you noticed, I try to be as much as possible independent from mentioning the fact that we have a jet in gamma ray burst, except when I discuss that the jet break in the light curve of the afterglow is a sign of the present, possible sign of the presence of jet. I would say that from a theoretical point of view, we do expect that these sources have a jet, because if we believe that the central engine is, for instance, a spinning black hole in accretion, or even a spinning highly magnetized neutron star like a magnetar, there could be some preferential direction for the extraction and injection of energy and challenging of the energy. By the way, there could be a role in collimating the outflow led by the magnetic field, or even by the external medium. Think about the fact that in long gamma ray bursts, the outflow is produced near the surface of, let's say, the last stable orbit in the proximity of the black hole, so far inside the progenitor star, which can have a radius of 10 to the 11 centimeter. And so the outflow has to travel through the, let's say, envelope of the star. And in this travel, probably there is an interplay so that the outflow itself is collimated. And the same could happen for short GRBs, and magnetic field can have a role. So I'm not going into the details of how the jet is collimated. I assume that the jet is present, and I show you what are the effects of having a jet in a gamma ray burst. So the first evidence, the first effect you have to understand is the fact that there is a difference between geometric collimation and beaming. Beaming is whatever is related to the fact that the source which is emitting photons is moving towards the observer with the bulk clearance factor of 100 or so. And so the beaming cone you can think about is roughly 1 over the bulk clearance factor. The collimation instead is the geometric aperture of the channel within which this relativistic outflow is expanding. I'll try to, let's say, clarify this with this plot here. So imagine that this is the cone, aperture cone of the jet, and this surface here is where the photons are emitted. You have now the clear idea that during the afterglow, the emission is produced by something which is decelerating as a function of time, and therefore its bulk clearance factor is decreasing. So at some point, in general, you have that you cannot see, if you are located along the axis, all the photons produced by this region here, but just those within the beaming angle, 1 over gamma. But since gamma is decreasing at a larger stage, you see a larger portion, it's not scaled, but forgive me for that, of the emission region, up to a point in which you have the equality approximately between the beaming and the collimation. 1 over gamma is the beaming, and theta jet is the physical collimation of the jet. From this moment on, even if gamma can still be decreasing, of course, you have no emission outside the jet opening angle. So you see all the radiation, or all the surface emitting photons. And you can imagine that, also naively, this time scale, this characteristic transition is going to imprint some change in the light curve. And the change is basically a steepening of the light curve. This is a prediction of the model, which is met by the observation. I show you here just a couple of examples. This is a light curve of a GRB dating back to 1999, where you see that there is a transition. This is smooth, of course, because this is an oversimplified description of the process. There is a smooth transition from a decaying low to a steeper one. And by measuring the time when this transition happens, this is another example, okay, what you have is that similarly to what we did with the bulk clearance factor, you can derive an estimate of the jet opening angle. It's simply by combining the simple equations, okay? And what you get is an equation like this. This is valid for the interstellar constant density interstellar medium, the observable you need are the energy of the prompt, let's say the energy of the afterglow, which is the kinetic energy during the afterglow phase, the density of the interstellar medium, and again, the time when where you observe this break here. Typical values of the break combined with the other observables allows us to derive the typical opening angle of GRBs. So in this plot here, I show you a comparison of the opening angles of GRBs for long and short GRBs. Now, there is clearly a great difference in number because we have much more, though not that much, measurement of the opening angle for long GRBs and very few for short GRBs. The reason, I think, is mainly related to the fact that the afterglow short GRBs is in general dimmer than long ones because the scaling factor is basically the total energy involved, as I showed you in the first slides before the break. And therefore, since the jet break transition happens typically around a few days, and in order to measure it, you need observation before, which are okay, the source is still quite bright, but even much after the transition, when the source is extremely dim, it's a challenge to measure this transition. And however, for the bursts, for the long ones, for which this was possible, the distribution of the jet breaks spans between a few degrees up to a few tenths of degrees. It's a log normal distribution with a typical peak around 5 degrees. For short GRBs, as much as we know, it seems that is not that far from, or not that much different from that of long GRBs. The implication of the fact that GRBs have a jet, of course, is the first one on the energy. So far, we have been describing, also in the correlation I showed you at the beginning and so forth, I've been always using the isotropic energy, which is called isotropic equivalent energy. Indeed, the term equivalent stands for the fact that we use it as a proxy of the energy of the burst, but doesn't reflect the real geometry of the outflow and therefore the emission. So if we want to be a bit more precise, we should take the isotropic energy or luminosity and correct it for the opening angle, which is a factor 1 minus cosinus of the opening angle. For small angle approximation is a factor theta square, basically. And the reduction can be, given the values that you see here for the opening angle, even of a few hundred. And what happens is that, for instance, you see in this histogram that there is both effects of a shift of the typical peak of the energy or luminosity when you consider the angle correction, so the true energy, to a value which is 10 to the 50, 10 to the 51. And there is, if you can appreciate it, also a reduction in the scatter, okay? Okay, now, what are the effects that the jet has for the observed properties? They can be very dramatic. Probably you experienced studying 1708-17, and let's say that they can be very dramatic because the observed quantities now depend on the fact that we have a jet, and so what we see depends on the orientation of the jet with respect to the line of sight, and the material inside the jet is moving at relativistic velocity. So we have the combination of, we have to take into account the combination of the two effects, the geometric one, which is the orientation of the jet, and the relativistic ones, which depends on the bulk Lorentz factor. I try to explain this with this slide. So here I draw a jet, which I assume it's a conical jet, within which the material which is producing radiation is flowing with the bulk Lorentz factor, which is constant within the jet and independent on the angle you consider within the jet, okay? The comoving frame intensity is this quantity, which is primed, okay? And for the relativistic transformation, for instance, if you are at large viewing angles, okay, with theta view, the viewing angle much larger than the opening angle of the jet, you have that the Doppler factor that you have to compute is this equation here, okay? When you go on axis or within the jet, close to the jet axis, you have that the equation becomes this one. So by taking the ratio between the off-axis with respect to on-axis Doppler factor, you can understand if you have a brother, you're looking the jet from off-axis, and your brother or friend is looking that from within the jet, you can compare what you see. And this ratio is telling you how your view and the information you see depends strongly on the combination square power, you see, of the bulk Lorentz factor and on the viewing angle. So the very simple argument you can do, for instance, is comparing your luminosity that you observe. Since the intensity from the comoving frame to the observer frame scales as the Doppler factor to the cube power, you have that the luminosity at any time for a given theta view, for a given viewing angle, is equal to the luminosity that your friend would detect if located on axis, times this ratio to the third power. And since in the prompt phase, as we now know, the gamma factor is constant, the only dependence then is for the viewing angle. So what you have, if you make the measurement with your friend and compare moving yourself at different viewing angle, what you get is a curve like this. This curve describes indeed the ratio between the energy, luminosity, whatever quantity you want to measure related to the luminosity or the energy at a given viewing angle with respect to the on-axis one. So by moving at larger viewing angles, you see that there is a dramatic drop. So if I am observing within the opening angle of the jet, which in this example is 3 degrees, I see, let's say, the maximum of the emission, okay? Modulus, this is boosted by a factor gamma square with respect to the moving one. But as soon as I move outside, you see that I can have within a few angles, so a few degrees of axis, a reduction which can be even of 6 orders of magnitude. So this is dramatic. Of course, the shape of this fast decay is related by the parameter, which is the bulk Lorentz factor that we fix. The larger is the bulk Lorentz factor, the steeper is this decay. The smaller the bulk Lorentz factor, the shallower this decay, okay? What happens now if we think about this argument for the afterglow emission? For the afterglow emission, we have simply to consider that gamma is not constant. The equation is, again, similar. Okay, there are some complications because one has to take into account the delay of the arrival of photons emitted by different regions, okay? But in general, the, let's say, take-home message is more or less represented by this plot. Here you see an afterglow light curve simulated. So what an observer would see if located within the jet is the typical power law decay of the afterglow light curve, which is represented by these lines here, okay? And now if you think about going, comparing, let's say, with respect to the on-axis light curve, what happens if you observe at larger off-axis angles? It happens that because of this strong dependence on the debeaming effect and let's say the decrease of the bulk Lorentz factor as a function of energy, at the beginning you see very low emission of the afterglow because look at the plot, all the emission of the afterglow is beamed in this direction. But as gamma decreases, at some point the beaming angle, so 1 over gamma approximately, becomes equal to the viewing angle. And then you see basically the peak of the afterglow. So you reach basically the afterglow emission that an observer on axis would see. From that moment on, you and your friend on axis do see the same temporal decay of the afterglow. Okay. So if I don't know if I still have 5 minutes.
5 minutes you have. 5 minutes you have, yes. So would that,
okay, so because I have just the last couple of slides which are related to the jet, which are propedeutical for tomorrow in a way. Probably you can I?
Sure, you can go ahead, and I think it makes sense to finish this part. Yes.
Okay, so what I just want to mention at the end of this lecture is something which is useful to understand probably what we will see tomorrow, which is the fact that you have been hearing quite a lot probably about structure jet, which became popular, I would say, quite a lot starting in 2017. Let me say a bit what is the genesis of this concept. In the example I showed just now, and to understand, let's say, the basic properties of GRBs, what we have been dealing with typically is what we call a uniform jet or top-hat jet. What is that? As I described, is a jet in which basically the energy content and the velocity of the material flowing within the jet is independent from the angle, okay, from the positional angle within the jet. This model, which has been used for years in describing GRBs, their afterglow and the population in general, if you want to describe the diversity of GRBs in terms of total energetics, of afterglow behavior, even prompt emission properties, you have to ascribe in a way the different GRB properties to the different opening angle of the jet as the distribution that I was showing before. Think, for instance, to the relation between the true energy and the isotropic equivalent. Since the true energy is the isotropic equivalent times theta square, and as I showed you, this is almost constant or is very narrowly clustered around the typical value of 10 to the 50, 10 to the 51, you have that there is an anti-correlation between, in principle, the isotropic energy and the jet opening angle. Larger angle corresponds to lower energy, smaller angle corresponds to larger energy. Starting in 2002, people started to think about, let's say, starting in 2001 to be precise, in this paper by Lipunov, people started to think about, instead of having a, let's say, very simplified uniform jet, having a kind of structured jet in which you can think about nesting different jets with different properties in terms of energy and bulk velocity, one within the other, co-aligned, okay, with the same axis. And what comes out is the prototype of the so-called structured jet. What is the nice point here is that with the structured jet, much like what happens for instance, AGN, you have the, let's say, possibility of describing now or ascribing the GRB diversities to a different viewing angle rather than a difference in the intrinsic properties of the jet. This is why it is sometimes or often, let's say, often called also universal jet, because with the universal jet structure or with some, let's say, dispersion in its parameter, you can account by just moving the jet at different viewing angles, which is random, of course, in the plane of the sky. You can account for the GRB diversity. And starting in 2017, we started to, let's say, work with the nomenclature, which I think became a bit complicated by the fact that we started to consider structured jet plus cocoon, uniform jet plus cocoon, structured cocoon, and so forth. I think these are all valid, and probably there was at the beginning a bit of confusion because of the different use of these terms, but in general they are very, let's say, realistic in the fact that, let's say, while this model here is very simple and can catch the, let's say, gross feature of the observed properties, what one should expect from a physical point of view is a much more complicated situation where you have a jet with some angular structure, with maybe some sheet around, which can be relativistic or mildly relativistic in the form of a cocoon, whose physical origin is different. Of course, by complicating the picture, also the description of the data, the modeling of the data can become a bit more complicated. I have two slides, but just two left slides. Just tell me, I can also take this at the beginning of the lecture tomorrow. It's up to you. I don't like when I'm late.
Well, yes. So well, maybe this is a good thing for a refresher at your at the lecture tomorrow, so that you can summarize and conclude on this part.
Okay.
Do you have a final word? I mean, maybe you want to jump to the very conclusion of your talk, and maybe we can do this tomorrow as you want.
Well, okay. So frankly, I have no concluding slide because it would be a long list of concepts. So sorry, not today, neither tomorrow. I have a concluding typical conclusion slide. But if there is any question, maybe it's worth taking it now.
So let's see.
I hope the only final word, if I may, I want to say is that again, I hope giving a lecture of a couple of hours on GRBs, trying to capture all the physics, is an ambitious project. I hope I just reached the minimum level, and I was not too much confusing in giving you these concepts, and I was clear enough. As you said, Eric, there are references for understanding much better these concepts.
Very good. Let's see whether there are questions. And so maybe people start to be hungry, or yeah, 2 hours and a half is a long lecture. I don't see any hand up or thing, but maybe we should give some time for the people to digest what you say, and possibly they will come up with question at the beginning of next lecture tomorrow. So I think we should conclude here for today. We had a number of questions while you were talking earlier, so I don't worry too much. Let's reconvene therefore tomorrow with this lecture I think it's in the morning again, right? So you'll be talking tomorrow morning. Thank you for joining today, and let's close here. I should close the recording.